Ashland resins are well known for providing reliable, durable, real-world performance. To achieve this performance, it is important to properly apply the product. Ashland's technical service team regularly provides troubleshooting and process guidance to composite manufacturers worldwide. This video will outline best practices for lamination with Ashland resin, which will provide lasting value to the end user. As a responsible care company, it is critical that we begin by ensuring our materials are applied safely. Be sure to follow all safety procedures outlined by OSHA and your manufacturing facility. Before working with resin, review its safety data sheet, take note all safety precautions, and use PPE recommended by the safety data sheet. PPE. To safely work with resin, eye protection and gloves should be worn at all times. A respirator and protective clothing should also be worn at the worker and manufacturing facility's discretion. Gel coat cure. Before preparing for the lamination process, check the gel coat layer to ensure it is properly cured. It should either be dry or have a slight tack on all areas of the mold. Allow for at least 90 minutes of cure time at a temperature of at least 21 degrees Celsius or higher. Proper airflow is important for gel coat to cure properly. Because styrene vapors are heavier than air, these vapors can lie in low areas of the part and cause undercured or wet areas. Resin mixing procedure, bulk and drum. Before you begin, make sure the resin has been properly agitated. The procedures for mixing bulk and drum resin will differ. Bulk resin should be mixed twice per day for 30 minutes at a time. Drummed resin should be mixed before use for at least 15 minutes. You may need to use a higher speed for the first 3 minutes to get the material moving. You can then lower the speed after the first 3 minutes. Record the date, resin code, resin batch numbers, and operators on the laminate documentation card. Contamination. Regular maintenance to your gun filtration system will help avoid contamination. An air drying system and water separators should be used to remove oil or water contamination. These traps should be drained daily. Before spraying a part, open the traps and verify that they have been drained. Temperature. Check the temperature of the resin, ambient air, and the mold with an IR gun. Record each temperature on the laminate documentation card. Ensure that all temperatures are above 21 degrees Celsius. Catalyst selection. It is strongly recommended that before using any catalyst and resin combination in an application, the fabricator should confirm that the catalyst and resin meet the manufacturer's specifications. Different brands of similar catalysts have shown to react differently with the same resin system. Typically, methyl ethyl ketone peroxide catalyst can be used for most applications. MEKP catalysts yield a rapid resin cure development. Cumene or cumene blended catalysts tend to increase gel time, slow gel to peak, and decrease exotherm, although it typically yields equal or greater degree of cure after 24 hours as compared to MEKP. Other specialty catalysts, or combination of catalyst types, can be used for specific applications. They can speed up or slow down the gel time, gel to peak, increase or decrease exotherm, and improve thin film cure. Please consult Ashland Technical Service for recommendations on the type of catalyst to use in your process. Most chopper guns mix catalyst and resin internally. On an internal mix unit, the proper catalyst pressure is influenced by the pump ratio, pump pressure, and viscosity of the material being pumped. The pump ratio will either be 6:1 or 7:1. A typical catalyst pressure range would be 17 to 27 bar. For example, if you have a 7:1 pump and a pump pressure of 3 bar, the catalyst pressure should be in the range of 21 bar. You will need to follow manufacturer specifications to verify the correct catalyst pressure specs. Be especially careful with new O-rings. If at any time you see the pressure dropping, it indicates that you are losing back pressure, which may cause inconsistent dispersion of catalyst on each pump stroke. You can verify catalyst line pressure is correct by checking its gauge. Dyed catalyst can also be used to ensure the correct catalyst pressure is set or catalyst and resin are mixing properly. It's crucial to use the proper amount of catalyst. Always verify that you are using the proper catalyst percentage before spraying a part. The recommended catalyst range is between 1.25% to 2.5% for Ashland resins. The skin coat typically runs at 2% catalyst to help achieve a faster cure and higher barcol. Bulk laminate and coring materials normally run at 1.5% to keep exotherms low and allow cure to develop slowly. This will lead to improved cosmetics. Adjust catalyst levels to get proper working times in mold for ambient conditions. Record the amount of catalyst used on the laminate documentation card. Glass reinforcement selection. There are many different types of reinforcements, including E-glass, S-glass, aramid fibers, and carbon fibers. These materials come in many orientations and sizes. Laminate reinforcement will be dependent on the part requirements. Chop strands or chop glass should always be used in the skin coat to facilitate an even layer without air voids. It may also be used in other areas as determined by engineering or the laminate schedule. Generally, woven roving is used to add strength and reinforce high-stress areas due to the weave pattern and the size of the strands. Structural, stitch cloth, knit cloth, and other weave patterns are available and provide similar performance. Engineering will determine where to use any or all of these materials within a laminate. Both woven and structural mats should be applied after the skin coat has reached a 934 barcol of at least 20 to 40 for cosmetics and bonding. Core mat material. A wide range of core materials can be used in a composite part. Most cores are used to add stiffness and strength, as well as reduce weight within the laminate. Core materials can also be used for screw retention. Core types consist of balsa wood, different density foams, such as PVC and urethane, spun fiber materials, and marine-grade plywood. The engineering team for the facility will determine the appropriate core for the part being built. Using a balanced laminate on each side of the core will strengthen and stiffen the laminate and produce the best results. For guidance to properly wet out or bed core materials, follow the best practices recommended by the core manufacturer or contact Ashland Technical Service. Types of equipment for hand layup and rollout. Laminate consolidation is essential to make a quality part. There are different types of rollers for different jobs. For skin coats, a finish roller should be used. Bubble buster rollers are better suited for the second skin or bulk laminate layer. This type of roller has become widely and sometimes overly used in the open mold FRP industry due to their ability to easily compact the laminate and remove large air pockets. However, they can leave resin-rich lines on the part, which will transfer to the cosmetic surface. They can also leave fine air in the laminate that can create rework and warranty issues, like blisters, in skin coats. It's best to use them only for bulk lamination. The diameter of a roller is as important as the type. There are various diameters, which will fit into different radii of the part surface. Using a roller with a larger diameter than the radius that you are rolling will cause resin to puddle in the radius next to the gel coat. This will cause excess shrinkage, which in many cases leads to print problems and heat lines. This resin-rich area can also lead to a weaker part of the laminate that is prone to cracking. Spray pattern development. Once you have selected all the proper materials and equipment to build your part, you are ready to begin applying the material. First, verify the pump pressure of the spray gun. The chopper gun tip selection should be matched to the cutter speed and number of glass strands of the chopper gun to ensure that the correct glass-to-resin ratio is achieved. 2 strands will use a larger tip than a single strand. Start with low pressure and incrementally adjust the pump pressure up to the lowest possible pressure that will support an even pattern. Position the chopper motor to evenly distribute the glass into the resin stream. The glass usually intersects with the resin approximately 15 to 20 centimeters from the sprayer tip. Adjust from side to side to ensure the glass is hitting and dispensing the pattern evenly. From here, adjust the cutter head speed to obtain proper glass-to-resin ratios. Use a disposable surface, like booth paper or cardboard, to observe and adjust the glass and resin distribution prior to spraying the part. Glass calibration. Ensuring the correct glass-to-resin ratio is critical to manufacturing the best quality parts. First, weigh an empty bag to zero the scale. Tie plastic bags to capture the resin and glass separately. With a timer, spray the gun for 15 seconds, capturing the resin and the glass in their respective bags. Next, weigh the bag of resin and record the weight. Use the same weighing procedure to determine the weight of the glass. Weigh an empty bag to zero the scale. Weigh the bag of glass and record the weight. Use the weight of the resin and the weight of the glass to calculate the resin-to-glass ratio using the following calculation. Glass ratios typically run 35 to 40%. A higher glass content reduces issues with heat or shrink lines and produces lighter and stronger parts with better cosmetics. It is very important to use the correct ratio of resin to glass. Using the incorrect amount of glass will alter the strength of the laminate and can lead to an increase in cracking. It can also cause a variety of rework issues, such as excessive sanding and buffing, to remove cosmetic defects. Proper spray techniques. Inspect the spray pattern and make sure the glass is not being thrown outside of the resin pattern. Use the proper spray technique of cross-hatching the glass up and down and side to side as you build the layers to proper mill thickness. Overlap each stroke by approximately 50%. This will ensure a more consistent laminate. Have an operator check mill thickness with a laminate mill gauge as the part is being chopped to ensure uniformity of the laminate. Laminates that are too thick are difficult to roll out, which can lead to air voids. These air voids can cause weak points in the laminate and can lead to excessive and time-consuming rework. Thick laminates may also cause fiber print issues on the part. Skin coats that are too thin will not develop barkle hardness properly and may allow the bulk laminates to print through the skin coat. With a thin skin coat, fibers may be difficult to roll out around edges and corners. Proper skin coat application and cure. The purpose of the skin coat is to create a first layer of reinforcement behind the gel coat. It should be free of air voids and creates a hardened layer to help block fabric print from the addition of other layers of fiberglass reinforcement. Proper skin coat thickness is an engineering and company preference, depending upon the quality and weight recommendations. A proper skin coat can be anywhere from 600 grams per meter square at 1.5 millimeters and 900 grams per meter square at 2.3 millimeters, depending on the design. The thickness of the skin coat should be even throughout the part. To avoid creating thin or thick areas on the part, use proper cross-hatching techniques while applying the material. A laminate mill gauge should also be used in several different spots on the part to verify thickness and uniformity. A thicker skin coat of 2.3 millimeters is recommended to create the best print protection. Skin coat applications exceeding 2.3 millimeters are not recommended, as it is very hard to roll and eliminate the entrapped air. The skin coat should also be well cured prior to applying bulk laminates and other reinforcements. It should achieve a 934 barkle hardness of 20 to 40 before bulk laminate application. A higher barkle reading on the skin coat indicates a more thorough cure, which will help ensure good quality cosmetics. Record the catalyst type and level, laminate thickness, glass type, and barkle on the laminate documentation card. Proper bulk laminate application. Once the skin coat has achieved the proper barkle hardness, the main laminate can be applied. Bulk laminates will vary with build schedule and part type. Using heavy laminates on an undercured skin coat or too much glass at one time can cause excessive heat and print in the laminate. Structural layers should be back wet for faster and sufficient wet out of the fibers. Using the correct roller for the part's geometry, the structural layers should be rolled out well, removing all air from the laminate and compressing the layers. Excessive resin should be removed with a squeegee or paint roller. Record the catalyst type and level, laminate thickness, and glass type for the bulk layer on the laminate documentation card. Laminate cure. Cure of the laminate is affected by catalyst type and amount, air temperature, resin temperature, mold temperature, laminate thickness, and lamination process. Consult with Ashland Technical Service in order to achieve the ideal laminate cure. Use a Barcol 934 to check the bulk laminate's hardness. The ideal hardness is between 30 and 40 Barcol, depending on the part. Before demolding a part, take a temperature reading. The laminate temperature should be at ambient or room temperature. This ensures that the parts are cured and have enough green strength to be pulled. Record the Barcol at demold on the laminate documentation card. Proper demold process. To begin demolding, use plastic or wood wedges to gently break the sides of the part loose from the mold. Avoid using metal tools during demold, as they can damage the part and the mold. Be careful not to flex more than necessary, as this can cause damage to the mold and the part. With the wedge in place, use regulated air pressure to blow air between the open space between the mold and the part to help break it loose. Do not use air pressure above 2.5 bar for demolding parts. Continue to do this on all sides of the part until it is completely loose from the mold. You may need to add bracing to the part near lifting points to ensure pressure is applied evenly when lifting with a hoist and make sure the part does not overflex, crack, or bind in the mold during the pulling process. This is best determined by observing the pulling of a few parts and finding the problem areas. Apply even pressure on the lifting hoists for easier demold. Using excessive force can stress parts, which can result in cracks developing as the part ages. In extreme cases, parts can actually be cracked during the demold process. Some parts may be more challenging to demold due to part design or a slightly negative draft. Transfer of part. Use a padded cart to transfer the demolded part to the next station. This eliminates the chance of a finished part being dropped, reduces lift fatigue, and protects the gel coat from being scratched or damaged. Thermal cracking. Scribing and countersinking are done to reduce the propagation of cracks from fasteners. A metal screw is a poor insulator and has a thermal conductivity much greater than the composite laminate. As a result of thermal cycle exposure, the metal experiences a more rapid change in temperature, which leads to a higher rate of expansion and contraction relative to the composite material. The difference in the rate of dimensional change between the metal and the composite laminate can induce stresses that promote crack formation. Countersinking screws will reduce stress on the laminate and reduce the chance of crack initiation and propagation. Small cracks created by non-countersunk screws often propagate under stress at low temperatures, causing costly warranty issues. The interface between the gel coat and the laminate can allow these cracks to propagate, as it is a non-reinforced resin-rich layer. Countersinking screws will ultimately minimize the risk of chipping and cracking in both the laminate and the gel coat. Another technique to avoid crack propagation is a scribe line. Using a Dremel tool, cut completely through the gel coat and into the laminate. The scribe line will give a surface crack a stopping point if a crack develops from a screw, as it disrupts the non-reinforced interface layer. The most common place to put a scribe line is on the deck and hull between the area where the two will be screwed together. The scribe is then covered up by a rub rail. The disruption in the gel surface will help keep the crack from extending past the cut line onto the main surface of the deck or hull. Trimming and cutting. Diamond wheels, hole saws, and router bits are recommended for trimming and cutting to create the smoothest edge of the fiberglass surface. These tools will give the best cut to avoid chipping of the gel coat or damage to the laminate. Be sure to monitor the blade itself and ensure that it remains sharp at all times. A dull blade will severely affect performance. Carbon steel drill bits should be used in conjunction with countersinks, as all holes drilled need to be countersunk and remain smooth with minimal damage or chipping of the gel coat. Chipping of the gel coat around the cutting surface is an indication of a dull cutting tool or too much manual force being applied. As with fasteners, chips in the gel coat caused by an improper cut can start the initiation of a fracture in the gel coat or laminate at the cutting surface. Stresses applied to the laminate can cause these fracture initiation points to propagate through the resin-rich interface between the gel coat and skin coat under extremely cold conditions. The proper lamination techniques outlined in this video will assist manufacturers to laminate parts with unmatched quality, aesthetics, and performance. For additional lamination recommendations, please contact Ashland Tech Service.